Okay, this is part 3 of our vector calculus study, and we are here now. And actually, we're not going to do this. Of course, if you want to read this, you can. These are examples of parametric equations and examples of uses of parametric equations. Okay, so for homework for this section, let's see. So for homework, do 1 and 3 here, 7 and 9 here, and number 13 here, and one more, number 22. Okay, now let's review the dot product. We've covered this in our class already, but if you have a vector A, looks like this, and a vector B that looks like this, the dot product is you take this element times this element plus this element times this element, and so on. So it's A1 times B1 plus A2 times B2, and so on. So these vectors are in R3, so you can have 3 terms here. Okay? And in R2, you're only going to have 2 terms. Okay, now one thing to notice is that the dot product is between 2 vectors, so it's a vector on the left of the dot and a vector on the right of the dot, but the answer is not a vector. Right? This is not a vector, this is just a number. Right? So the dot product of 2 vectors gives you a number. So it's a very simple operation, but it turns out to be quite useful. So suppose we have this and this. We want to know the dot product of these two. So it's 1 times 2 and so on. You get 15. Here, if we express the vectors like this vector, and this vector, the dot product, again, it's 3 times 1, 2 times 2, and, no, sorry, j is 2 times 0 and negative 1. So you get this, and you get that. Okay, dot product. So it's also called a scalar product. Okay, and it says, takes 2 vectors, one on each side of the dot, and gives you a real number, not a vector. Okay, some of the properties of dot product are that if you take, if A, B, and C are any vectors, and k is just a scalar number, if you take A dot A, it's never going to be negative. And let's see, how can we show that? So if this is A, if you take A dot A, you're taking A1, A1, A2, A2, A3, A3, that's A1 squared. This sum is never going to be negative. So we proved that this is true. And also we can say that the only time it's going to, A dot A is equal to 0, that is the only time this is going to equal to 0, is if all these terms are 0, that is if all these are 0, so that means that A itself is 0, the 0 vector. Okay, A dot B equals B dot A, that's very easy to prove. Let's see, do they do it? No. But these are easy to prove, and this is like a distributive property for the dot product, and the addition of vectors, and Ka times B, or sorry, Ka dot B equals Ka dot B equals A Kb. Okay, so you can you should be able to prove these yourself, but we won't worry about that. Okay, another one is we're going to define now the length of A. So up to now we really haven't had any meaning for the word length. Now, actually that's a little bit wrong, because I already said that the length of A, when you think of A as an arrow in the plane, then of course we know what the length of an arrow means. So we do know it in that sense, but divorcing it from the idea of an arrow, then we don't really have any concept of length for this vector A. But now we're going to give a definition for the length of A, and hopefully it'll mean the same thing as the length of the arrow when we have an arrow. You know, we don't always have an arrow. If we're talking about in 3 dimensions we can have an arrow, in 2 dimensions we can have an arrow, but in 10 dimensions we don't really have an arrow, but at least when we're talking about 3 dimensions, our definition that we're going to give here hopefully will give the same answer as what you would say is the length of the arrow in 3 dimensions. Okay, so anyway, what do we mean by the length of A? The length of A is defined to be this. Well, actually, that's exactly the same idea as the length of the arrow, because this is just from the Pythagorean theorem. So anyway, this is the notation for the length of A. Later we're going to call this the norm of A, and we did that in our class before already. Anyway, later we're going to call this the norm, but right now we'll just call it the, or they also call it the norm, or the magnitude, or the length of A. Okay, now what is this though? Well, I think I just saw this before. I just saw this. So what is this? Well, this is A dot A. So another way to say that the length of A is to say what? It's the square root of A dot A. Okay? So that's what they say here. The length of A is the square root of A dot A. You can read this here and see that this is basically just the Pythagorean theorem. Okay, or you can say it this way, or you can square both sides, and then you get this squared, which is here, squared, is A dot A. So the length squared, or the norm squared, is A dot A. Okay, now remember, A dot A is a number, not a vector, right? A is a vector, but A dot A is a number, and this is the square of the length, or the square of the norm. That's also a number. Okay, next, here's A, and here's B. So this was A dot A, but now we're talking about an A and another vector B, and talking about their dot product. And A dot B turns out to be equal to the length of A, the norm of A, the length of B, or the norm of B, times the cosine of the angle between them. So, is that right? Well, you know this actually from trigonometry, but you might not know it written like this, but you know this fact basically. But let's test this out in 2 simple examples. So suppose that A and B are the same. So then instead of A dot B, we have A dot A. We already know that A dot A is here, right? So, and what's the angle between A and A? So it's obviously 0. And what's the cosine of 0? It's 1. So if we do A dot A, what this is saying is that it's the norm of A times this is still the norm of A. So this is the norm of A squared, and this is 1, but we already said that. So in the case where B is A, B and A are the same, then this just becomes this. So okay, at least in that case we can see that this is true. Now one other case that we could look at is, what if A and B are perpendicular? Then what about the cosine of the angle between them? So that's the cosine of 90 degrees, and that's 0. So in that case, A dot B is going to be 0. Now that may not be intuitive. I mean, you may not know, that's not, we don't know enough about the dot product to say, oh yeah, of course that's true. But let's take a look at that also. Anyway, let's see, how do we prove this fact? Because this is really important and very useful. So how do we prove it? It's useful because later on, in a few more, if I scroll down just a little bit, we can rewrite that after we've proved it as this, basically, which we'll see in just a second. So that tells us what the angle between A and B is. So let's just look at that in a minute. But first let's do this. Where does this come from? Where's the proof of this come from? So actually they're going to take a special case. In the case that either A is 0 or B is 0, then what? Then if, say, A is 0, then A equals this. And so A dot B is going to be 0, right? And what's this going to be? I guess the angle between a vector and the zero vector is also, well, how do they do this? Oh, then this is also 0. So then this side is 0. So in that case, in the special case, when a is 0, why are we breaking it up into special case? I'm not sure, but it's true. In the special case, it's true that if a is the 0 vector, then this is true. Okay, so I guess they did that special case because they want to be able to say, okay, suppose that neither a or b is 0. Okay, then what? Let c be b minus a. Okay, we know, we looked at this before. Anyway, b minus a, we're going to call that c. Then we may apply the law of cosine. So this is the thing that I said we knew from trigonometry, which honestly I don't remember because it's been such a long time since I studied trigonometry. But I suppose you might remember it, or if you don't, you can figure it out. You can find it somewhere. So apply the law of cosines to the triangle whose sides are A, B, and C. So here's A, and here's B. Now we define C as B minus A. So now I always get confused. Is this going in the right direction or the wrong direction? And I have to check. If I want to check that, I have to say, well, what if I add A to this thing? So if I add A to this thing, obviously I get B. And that is if I add, so this thing is here. If I add A to it, I do get B. Okay, so for me, I just confirmed that the direction is from here to here. So you can confirm it yourself. Okay, so anyway, so there's this law of cosines, which says, we know for a right triangle, we know that a squared plus b squared equals c squared, but if it's not a right triangle, then we have this other thing called the law of cosines, which says that c squared equals a squared plus b squared minus this other piece. So we're supposed to remember that from a long time ago, or maybe it wasn't so long ago, but we're supposed to remember that. Okay, so we assume that this is true, according to the law of cosines. Thus this, so we can just take this piece and write it like that, but this is a dot a, this is b, so this is b dot b, and this is minus c dot c from equation 1. Now use the properties of the dot product. Since c equals b minus a, that's b minus, so c dot c, which is here, this term, is b minus a dot b minus a. And then we can write that as, where does that come from? I guess they're taking, they're taking b minus a times b, and then b minus a minus, or times a, and then putting the minus sign in front. So this is the distributive property that we accepted before, which was this one. So this one gives us this one. It gives us that. So then we get, then we multiply it out. We do it again, the distributive property here and here. We get this. Okay, so that's c dot c. By properties 3 and 4 of the dot product, so where are those? 3 and 4, this one and this one. Sorry, that was that. If we use equation 3 to substitute c dot c, we take this and we put in c dot c, we get all this. And now I guess some of this simplifies like b dot b minus b dot b. And so you end up with this, which gives you this, I guess. So, by property 2 of the dot product, okay, by canceling the factor of 2 on both sides, here and there, the desired result is obtained. Okay, so then we get this result, supposedly. Okay, is that true? Yeah, I guess so. Okay, so now we have this result, right? That's what we got. Okay, so now we have this result. Now we can just move this part down to the, divide it and put it underneath here, and then take the, what's that called, the inverse cosine, and that will give us just theta on one side. So like I said, this is important because now we can talk about the angle between two vectors A and B. So here's an expression for the angle between two vectors. It's this. Okay, now these vectors don't have to be, this is like, let's see. Okay, so we now have that. I was going to say something wrong, but anyway, we now have in R2 or R3, we have this expression for the angle between the two vectors. And for somebody who's sort of worried about something about the inverse cosine having two possible different outputs, they say don't worry because theta is defined to be between 0 and 2 pi. Okay, so if that bothers you, you can check out what this means. Okay, otherwise you can ignore it. So here's an example. Here's A, here's B, and we can get the angle between them by doing all this stuff, and we finally get the angle between them as pi over 3. So if this is a vector A and this is a vector B, and we go through all this stuff, then we find that the angle between them is pi over 3. Okay? And like we said, if A and B are non-zero, then theorem 3.3 implies that the cosine of the angle equals 0 if and only if A dot B equals 0. So, okay, whatever that means. Okay, it makes sense to call A. So in the case where the cosine of the angle is 0, that's when theta equals pi over 2. Hence, it makes sense for us to call A and B perpendicular or orthogonal when A dot B equals 0. And now we have a new word we can use, perpendicular vectors. Okay, of course we have that word in other parts of math, but now we can talk about two vectors being perpendicular when their dot product is 0, because that's when the cosine is 0. Cosine of the angle between them is 0, and that's generally called like pi over 2. Okay. If A or B is the 0 vector, then we cannot use formula 4, and the angle theta is undefined. Nonetheless, A dot B equals 0. Okay. So the 0 vector is perpendicular to every vector. Okay, well, let's kind of keep that kind of weird fact in the back of our mind somewhere. Okay, then we have an example. I'll let you read that example. Next thing is projections, which we talked about in the last video or some video before. So we have a vector. So the projection of B onto A. So here's B, the projection of that onto A. That's what this notation means. Now, as I told you in another video, I get confused by that notation, and I think, is that the projection of B onto A, or is that the projection of A onto B? Because that wouldn't be the same thing. That would be like something else. Anyway, it means the projection of B onto A. So you need to remember that. Okay, so we can see that the projection of B onto A is going to be a vector in the direction of A. Even here, we can see the projection of B onto A is a vector in the direction of A, or the opposite of A. Okay, remember by projection we mean that if you took a light and shined it down here, where would it fall on this line? Where would the shadow start or end on that line? Okay? Now we want to get some results about projections. For example, I guess this result, or this result. So this says that, remember, the projection of B onto A is a vector, right? So it's a vector. That means we can take the norm of it, or the magnitude of it. So we're allowed to put these double bars around it. Okay, and then so we can ask, what is the length of the projection of B onto A? That's what this is asking. And they're going to show that it's equal to this. Now, this is not a vector, right? The whole thing, sorry. I can't seem to identify, to select it, but the whole expression here to the left of the equal sign is not a vector. The stuff inside is a vector, but once you put the norm around it, it's not a vector, it's a number. So this better be a number also. But a dot b is definitely a number. If we take the absolute value of that, that's still a number. And this is the norm of a, so that's also a number. So at least they're both, this and this are numbers. But anyway, this is an expression for the size of the projection of b onto a. That's this. Okay, what else are we going to show? Not only are we going to show the size of it, as we mentioned once before, not only are we going to show the size of it, but we're going to actually have an expression for it as well. So this is not the norm of it. This is the actual projection, the actual vector. And here's an expression for it. Okay, so we want to prove both of these. But let's just, once again, this is a vector. How about this? Is this actually a vector? So let's check. Well, a dot b is not a vector. That's a number. So, okay, that's not a vector. This is not a vector. So this is a number over number. That's not a vector. So do we really have a vector? Yeah, because this is a number times a. But a is a vector. So, yeah, we have a number times a vector. That's a vector. So at least from that point of view, this makes sense, that this is a vector and this is also a vector. So finally, one more expression after we get to here is this. We can say the same thing. So this is a number, this is a number, number over number is a number, times a, though, times a vector is a vector. So this is another expression for the projection of b onto a. Okay, do we want to go through all of this? I'm not sure I want to. So instead of me going through it, I'm going to ask you to go through it. So where do we want to start from? From the idea of what we mean by projection. Get to, given this intuitive understanding, we find the precise formula for it. Recall that a vector is determined by its magnitude and its direction. It follows by definition that the direction is either in the same direction as a or the opposite, right? If the angle theta, okay, is between a and b is more than pi over 2, it's going to be in the opposite direction. Trigonometry tells us this. What? That the magnitude of the angle equals the size of this divided by what? B? The size of b. Okay, I guess that's from trigonometry. It looks pretty familiar. So I'll let you work that out. And this, and this, and I'll let you work all this out and get to, so make sure you go through this. I've gone through it too many times to want to do it again, but you should go through it. Make sure you go through this and get this result. Okay, so this is an expression for the projection of b onto, did I say it right? B onto a. So it's a dot b over a dot b times a. Sorry, I said it wrong. A dot b over a dot a times a. And the other result to remember is that the length of the projection is given by this. Okay, so I'm going to leave that to you. So here's an application in physics. We don't need to do that. So I'm not going to do that. I think this is in physics. Yeah, gravitational force. So we're not going to do, I'm not going to do that. You can look at it. Let's just read this though. This says that the norm of Ka is equal to the absolute value of K times the norm of A. By the way, why don't we have double bars here? Because K is a number. We don't put double bars around the number. Double bars are used for vectors. Okay? So anyway, this can be proved. And one more. A unit vector in the direction of a vector A is given by this. Okay, so if you, what is that? So is this really a vector, this expression? Because I just called this a unit vector, so it must be a vector. If they call it a unit vector, that's a type of vector. Is this really a vector? Well, A on top is a vector, divided by, this is what? A number. right? So this is a vector divided by a number, or a vector multiplied by 1 over a number. So yeah, that's a vector. And it turns out that this is of length 1. So let's see, let's try and show that, maybe. Proof of part 1. Okay. For part 2, we must check that the length of this is 1. Obviously, it's in the direction of A, but we want to make sure that it has length 1. So we want to look at this and look at its length, or the norm of it. And then I guess we can certainly do this. And then I guess by this property, we can take this part outside of that and put it over here, which is what they did here. So we get that. So we get 1. Okay. Unit vectors, that is vectors of length 1, are important in that they capture the idea of direction, since all have the same length. Part 2 of proposition 3.4 shows that every non-zero vector A, so you just start with a vector A, any old vector A, doesn't have to have length 1, can have its length adjusted to give a unit vector, U, by dividing A by its length. Okay, so A divided by its length gives you a unit vector in the direction of A. And they call it U for unit. This operation is referred to as normalization of the vector A. And then they give an example of where you might want to use that. But again, we're not going to do that. Okay, then they talk about vector proofs of some geometric results. Show that the line segment joining the midpoints here is parallel to and has half the length of the third side. So that this supposedly is parallel to this, and its length is half the length of this. So they do it in terms of vectors, and supposedly it's easy to do. So I'll let you look at that. And one more. So when you do this with vectors, supposedly it's easy to show these things. Show that every angle inscribed in a semicircle is a right angle. So if you do this, it's going to be a right angle. If you do it up here, you do it up here, it's going to be a right angle. Every angle inscribed in a semicircle is a right angle. So apparently with vectors, this is going to be pretty easy to show. So again, I'll let you go through that. Look at this. And they say vector proofs in examples 6 and 7 are elegant and sometimes allow you to write shorter and more direct proofs than those from your high school geometry days. Okay, some exercises to do for this section. So 1, 3, and 5, do those. Find the angle between do this one and this one. Projection, do 13 and 15. Anything else? Okay, so next video we'll do the cross product, and we're getting close to the end of chapter 1. We'll also do determinants and matrices. And some physics, we'll probably ignore that, like torque. But properties involving vectors, dot product, cross product, some proofs, And then we have equations for planes and distance problems, so we'll get to that later as well.